folks in the chat here. All right, let's get started. So as usual, don't forget the seating survey. It's Chem 112, section 001, ILC 118. Upcoming dates, tomorrow at 5 o'clock, the small group activity number 3 is due. I'm also going to be releasing an Excel spreadsheet and a tutorial video on how to use the Excel spreadsheet that is going to allow you to simulate some kinetic data that you will be able to then analyze to try to determine rate laws, rate coefficients, and those sorts of things. The tutorial will both go through how to use Excel in general for these kinds of problems and go through the specifics of how to take the data and do the kinds of analyses that need to be done on it. It's relatively straightforward to do. I will point out that you do need Excel in order to do this. Excel is available for free to students, and there is a link in the What to Expect Week 8 that goes through how to get it if you don't already have it. On Wednesday, as usual, the content videos are going to be due for this week, and there is the quiz over the small group activity on Wednesday as well. Friday, homework 7 is due, 3 parts. And as usual, Piazza participation cutoff on Sunday. Next week is when we're going to be releasing exam 2 on Thursday, due on Sunday. Exam 2 is covering kinetics and the first week of equilibrium, which is this current week right now. Do we have any logistical questions before we move on to some content? Okay, we'll move on to some content. Let's see. So, the muddiest points questions really kind of fell into 3 main categories. There's the small group activity questions, there's other kinds of kinetics questions, and then some questions on this week's material on equilibrium. Because the due date on the small group activity is the first due date we have, I think I should focus on that a little bit in what we're doing today. We will extend to some of the other topics as there is time and interest. So as sort of a background on some of this, there's been a request for the list of equations that are being used in the kinetics section. I have already started putting together a formula sheet for you guys for the exam. I should be able to have this complete probably today and have that posted for you. To give you an idea of what that's going to end up looking like, here we have most of the kinetics stuff on this side here. We have a discussion of reaction rates, of the differential rate laws, the integrated forms, the linearized forms, half-lives, and then some things about elementary reactions, activation energy, some comments on analyzing mechanisms, and then solution phase kinetics. So this afternoon, I'm going to be adding to this this week's material, the equations that are related to equilibria, and then I will get this posted this afternoon. There also was, let me see, last week on Thursday, I went through an extended example on analyzing kinetic mechanisms. The particular example is interesting because it was a given overall reaction, but which had two different proposed mechanisms. And so we analyzed both mechanisms to figure out what the rate laws would be from each of those, and then talked about how we would experimentally be able to tell the difference between the two. And so this was a sort of exam style kind of question that I went through in detail for analyzing these mechanisms. And so I strongly recommend taking a look at that example in the video on Thursday. If we end up not having enough material to talk about this week, today in class, I'm happy to go back and re-go over that if people would like me to. If we don't have time for that, however, do know that that's available on the video from Thursday. Okay. With that, let us talk about the small group activity sum. I know that based on questions on Piazza that there are a lot of questions that people are having about it. There are two I want to talk about briefly here, and then I'm going to do a little bit of a walkthrough of the various sections and the kinds of questions and things of this sort. So the first question that was asked was beta decay and alpha decay, specific instances of them, and how do you use them? So this is referring to the very top of the background material here, where we have two different decay mechanisms. Let's see if I can zoom in on this a little bit. There we go. Is the resolution good enough for the chat that you can actually see that relatively well? No, okay. What I will do instead then is I will call it up on screen and do a screen share. So give me just a second to get that set up. All right. Okay, I want to, oh, here we go. All right, screen share. All right, is that visible? Wonderful, okay. So just checking something on how I'm doing the screen share. I'm trying to have the chat window up as well for me to be able to see questions that come up. Is the chat window in the way of the document for you? It's not in the way. Good. Okay. All right. So the question was about alpha decay versus beta decay. So alpha decay, you're told, has a nucleus that emits an alpha particle, which is a nucleus of helium-4 atom. So that has 2 protons and 2 neutrons. And that's why we have, going from uranium to thorium, the mass goes down by 4 units from 238 to 234, and the number of protons goes down from 92 to 90. So anywhere you see an alpha decay, that's what's going on. You're going to have the drop in the mass of 4 and a drop in the proton number by 2. Beta decay, or beta minus decay, has the nucleus emitting an electron, which turns a neutron into a proton. So what's happening here is that the mass stays the same because the mass of the electron is negligible compared to the mass of the nucleus. But the number of protons goes up by 1 from 90 to 91, but the number of neutrons goes down by 1, which we see by the mass staying the same. Okay, so that's what the 2 processes are. The only place that you really use this information over the course of this particular activity is when we are looking at how do we measure this lifetime of being 4.4 billion years. And the comment that is made in the activity is that what we are doing is measuring the appearance of alpha particles. That we have a device, an instrument that can measure these alpha particles with close to 100% efficiency. So almost every alpha particle that is generated is detected. And so the point here is that we do the calculation to determine how many of these decays in the first in the uranium-238 to thorium-234, how many alpha particles we would get from that. And then we also then do an analysis over that same time frame of how many of the next decay particle we would see going from uranium-234 to thorium-230. And the upshot of those calculations is that the second decay produces almost no alpha particles over the time frame we're looking, compared to how many alpha particles we get in the first decay. So the only point that we have between these two is trying to look at comparatively 2 separate alpha steps in order to see whether we are indeed only getting the information from the first one versus getting some combination of the 2 from the first one and the second one. Beyond that, you don't really need to know anything else about that. So are there any follow-up questions about beta decay and alpha decay? Okay. So the second sort of general thing I want to point out is that there is in fact a typo in the activity. I have fixed it in the activity, but you may have made your copy beforehand, and so it may not be fixed in your version. Question 14 here originally referenced question 10, but apparently I had changed the numbering of the questions, and so this should be referencing question 13 for the information rather than question 10. Now, a thread on Piazza had said, should this be, 10 doesn't make any sense, do you mean question 12? And without looking too closely, I said yes. And then this morning I realized, no, it's not question 12, it's question 13. So know that, and know that it's supposed to be looking at question 13. Also, I am going to make sure that when I have the quiz set up to do the grading of things, I'm not going to ask you about question 14 and 15 for numerical answers, because I may have ended up pointing you to the wrong question. And so I'll make sure that those are not ones that, that are getting graded because of that. Okay. With that said, let me gauge the audience, both the chat and live. How many of you would like me to sort of walk through some of these questions to try to help you along the way of developing the answers here? Okay. All right, that looks like a lot of people that are very interested. And a lot of people in the chat say number 11. Okay, we can do that. So I do want to start here with the very first two questions, because they kind of form the basis for a lot of what you're going to be doing. So I'm going to do that relatively quickly. And I also want to talk a little bit about how you know what it is that you need to be doing on these problems. So the first thing here is to notice that it's talking about a first order process. So that means that we need to be using the first order rate laws that we have. There are three versions of the rate laws. There is the differential version, there is the integrated rate law, and there's the linearized rate law. Since this one is talking about solving for the concentration of an isotope, the standard integrated rate law is going to be the one that you're going to want, because it's already in terms of a concentration. So the first thing we will do is write down that equation. So I'm going to insert an equation, and what we have here is A equals A, and we need a subscript. So that's going to be this. A naught. Okay. We're going to need something here with a superscript, E to the minus KT. So that is our equation that we are working with. Now, a very convenient way to handle things within this document, when you're doing some sort of formula determination, would be to copy your formula, paste it in, and then make in the substitutions. So we are told that we want to deal with the concentration of the parent isotope P. So that just means we're going to call this P, we're going to call that P. Now we are also told that we want to have the expression in terms of half-life instead of rate coefficient. How did I create a formula? I went to insert and went down to equation. Are you able to see that on screen? Yeah, you're welcome. And when you do that, you notice this little bar that shows up here. This bar is where you can do things like superscripts, subscripts, fraction lines, things like that. Okay. Now, since the equation is asking for it in terms of half-life instead of rate coefficient, we need an expression that relates half-life to rate coefficient. So I'm going to insert another equation here, which is going to be the half-life equation. We need a subscript, T1/2 equals the natural, I need an equal sign, equals, we're going to need a fraction. So we need the natural log of 2 over K. Now, because we have a K in here, the most convenient thing to do is to solve this for K so that we can plug in. So I'm going to copy this down, solving it for K. We're just going to swap the position of the T1/2 and the K. So T1/2 comes down there. Oops, let's try that again. This side here becomes K. So now I'm going to show you why it is easy to do this copying and pasting this way. So I'm going to copy this down. I'm now going to say this is what K is, copy with the Control C. I'm going to select the K that we're substituting in for and paste. And so now we have our expression. And to make it convenient, let's put that T actually in the numerator right here, like so. So what we have now is an expression for the concentration of the parent isotope at time t, and all we plug in is the half-life and the amount that we started with. Okay, any questions on this step? Okay, so using your answer to question 1, so let's take our answer to question 1 and put it down here, okay? We want an expression for the concentration of the daughter isotope present at time t. So we need to remember this relation here. So let's think about what this relation is before we use it. This relation says that the daughter isotope concentration plus the parent isotope concentration added together equals how much parent isotope you started with. So the idea of this is that you have a parent isotope, each atom that decays turns into the daughter. So if this goes down by some number x, this goes up by that number x, and so the sum of the two has to be how much you started with. All right, given that, let's take this expression, and we notice that we have the parent isotope here, so that's what we're going to want to substitute out. So equation, insert an equation. So I'm just writing down what we have, and we need a subscript. Okay, now I'm going to take this one. I'm going to solve it for the parent isotope so that we can plug in easily to the earlier expression. Okay, so now we take this expression, and this substitutes for this. Okay, take that expression for the next step. We are trying to solve for this because it's asking us what an expression for the concentration of the daughter isotope. So let us subtract this from both sides. Let's multiply through by a -1. I'm going to rearrange this because it's usually more convenient to have things being subtracted rather than having the -1 in front. And then it tells you to factor out the P0 in your final answer. So oops. Nope, okay. Okay, all right. There we go. Okay, so hopefully this doesn't, this is just some very straightforward algebra at this point. So let's think about these two equations that we have in questions 1 and question 2. These are ways to determine, in the first case, how much parent isotope you have left after a period of time t. This one tells you how much daughter isotope has been generated at time t. So depending on which question you are being asked, are you being asked how much parent isotope is left, or are you being asked how much daughter isotope has been generated? That will tell you which of equations 1 or 2 you're going to end up using. So let's look at question 3 here. If you start with 1 mole of lead-206 and observe it for the observable age of the universe, how much of the sample would have been converted to mercury-200? So this is asking about how much daughter isotope you need. So this is going to be the equation you want. And I'm going to copy it down so that we can then substitute it in. So if you want to, you could take this and plug it in there. Of course, it didn't actually superscript like it should, but you get the idea. So I'm going to go ahead and leave this as a D for here, but if you want to be able to see it more clearly, you can certainly bring those down. So now we need to figure out what we are plugging in. So we have, we're observing it for the age of the observable universe, which is 13.8 billion years. So that is the time at which we are making the measurement. So time here is going to become 13.8 billion years. Now, it's not very convenient to type in billion years because units aren't going to cancel very well. So what we are going to do now is plug in what a billion is. So 10 to the 9th is a billion. And so then this is, right here is a multiplication step. So we can indicate that here with a times sign. So now we need to know the half-life. Our half-life, we are going from lead-206 to mercury-200. We have to go back to our background material. Lead-206 goes to mercury-200 with a half-life of 2.5 times 10 to the 21st years. So, oops, wrong one here. This half-life here becomes whatever I just said. I think it was 2.5 times 10, I need to do an exponent, 10 to the 21st years. Now notice that I am including in here the units. That's important because you need to make sure that your units cancel before you do the exponentiation here. That is critical for later problems because you're going to end up with cases where one of these may be years and the other one may be hours, and so you have to do a conversion. Well, you can do that conversion right here in the formula when you do it by dimensional analysis. Now, the last piece of information we need is our initial concentration. So we start with 1 mole of lead, lead-206. So we're going to put here 1 mole. Now, it's perfectly legitimate to say, wait a minute, that's not a concentration. Well, if we made it a concentration, it would be mole per some volume, right? Some volume V. Well, this then is going to be the number of moles of the daughter divided by that same volume. If I can get the cursor to the right place. Nope. Nope. There we go. So you can simply, if it's the same volume, you can just get rid of that, and now you're talking about amount. You're talking about moles. Shoot, let's try that again. So what we can, so that means that we can have the amount of the daughter just like this. And now it's just a question of plugging this in to Wolfram Alpha because a normal calculator will not be able to come up with the answer very easily. So it's important at this point to figure out how to write this in a format that Wolfram Alpha can use. And I'll show you how this works. So what we do is we take, it's going to be 1 times, I'm going to get rid of the units, so it's going to be 1 minus e, you raise it to a power, which you use the caret for, and I'm going to put parentheses in. Is going to be negative, and then the stuff in the numerator, 13 point, oh, I tried to use the numeric keypad and apparently numlock was on. So let me switch back there. I apologize for that. So, still, is numlock not gonna work for me? There we go. Okay, 1.3, no, 13.8. Used an asterisk for multiplication, same as you would in Excel, 10 to the 9th times the natural log of 2 divided by, and I'm going to put another pair of parentheses in here for the denominator so that we get 2.5 times 10 to the 21st. Once you have one of these expressions set up, you can just copy and paste and change out the numbers. So if I copy this and then come over to Wolfram Alpha, let me see if I can. So, oops, not plug it in there. So for the chat, when I switched to a new tab here, did it switch along with you so that you could see me getting to Wolfram Alpha? Wonderful, thank you. So click on Wolfram Alpha, and I'm just going to paste in what I just had. Hit enter. And it gives you an answer here, 3.8 times 10 to the negative 12th. So we come back over here. So we get 3.8 times 10 to the negative 12th. And I'm going to superscript that. And our units are moles. So the point of this calculation is that over the entire lifetime of the universe, if you start with 1 mole of lead, only 10 to the negative 12th moles of that, 1 trillionth of it will have converted to mercury. So this essentially doesn't happen. And so that is why it's reasonable to consider lead to be the end of the decay chain. Okay. So, any questions about how to do this calculation? Can we do 11 next? Yes. So the point I was going to make here is that the next calculations that are coming up here are exactly like the one we just did. So you can follow the model I just provided. Okay, question 11. Which is, yes, down here. Okay, so the first thing I want to point out on question 11 is that steps A through H are deriving an equation that you're going to be using from there on. And in step I here, I tell you what that result should have been. So you are able to keep moving on past this even if you don't get the derivation part correct. So you can take this as your answer and then move forward. That said, it is always worth understanding how where these things come from. This tells you to write down the linearized form of the first order integrated rate law. So let's do that. We are going to insert our equation, and the linearized form is the natural log of, I'm going to put square brackets from here, of the parent isotope equals the natural log. We need a subscript, and we need the brackets, parent isotope sub 0 minus KT. Okay, that's all there is for A. Write down the linearized form. Solve the equation for negative kt. Okay, so we're going to take this, copy and paste down. We are solving for negative kt, so I'm going to take this and subtract it from both sides. There. Okay, so I have a negative kt, and I'm going to now move this just to the other side of the equation so that it looks like we have solved for kt, negative kt. Okay, and we're done with that one. Oh, no, we're not done because we need to combine the two logarithms using this relationship here. So equals the natural log, oops, I'm no longer in the equation. Do an arrow and I'm now in the equation. So this now equals the natural log of a fraction. Come up here and we put in a fraction. Have p, oops, I keep wanting to use a down arrow to get to the bottom and that doesn't help, doesn't work very well. I'm going to do a subscript, p sub 0. Okay. Any questions at this point? So this is just doing the step that you're told to do. Okay. For reasons that will become apparent later, it's convenient to use base 2 logs rather than base e logs. So we now want to take this answer and write it in terms of base 2 logs using this relationship right here. So again, let's copy this down so that we have something to work with. We don't need the intermediate step. It looks like I have this in 2 separate formulas, so I'm going to get rid of that one and put it inside here. Okay. So now the relationship is that we take the, we have a new base that we want, which is the x. It can be anything we want. Whatever we're taking the log of goes into the log in the numerator. Whatever our original base was goes into the log in the denominator. So we are going to here put an equal sign. We are now going to, and we want log base 2, and it's going to be a fraction. So we need our log, I need to do the subscript so I get the base. So we want to have a log base 2 of something. And then in the denominator, we also need a log base 2. Okay, now coming back up, whatever we were taking the log of in the original case is what goes into the log in the numerator. So what we were taking the log of in the first place is this fraction. So that goes right here. Coming back up here, whatever the original base was is what goes into the log in the denominator. So our original base, ln means natural log, which means log of base e. So we put that there. We're now done with that step. Write down the formula for the half-life of a first order reaction. So that one is just something we've already done up above. Back in question 2, we wrote, in question 1, we wrote down the formula for the half-life of a first order reaction. So I'm going to copy that and bring it down. Oh, am I in the wrong? Nope, this is it. Boom. We are done with D. E. So, solve your answer to part D for K. That's this one here. And convert the logarithm to base 2. Okay, so we're going to take this down. We're going to solve it for K. So this is the same thing we did back in problem 2. I'm going to take that, oops, put it in the denominator. I'm going to move the K over here. Convert the logarithm to base 2. So we're going to use the same change of base formula we used before. And for convenience, I'm going to take this and copy it down here so that we can see our change of base formula. Okay, oops, don't want to change our numbering system. So what I'm going to do here say equals, copy this whole thing in, and we're going to replace natural log of 2 with this fraction here. Okay, now we just need to substitute in what are the x's and the a's and the b's. We are told that we are wanting to go into base 2, so the x's are 2's. A is the thing we were taking the natural log, we were taking the log of, so the 2, so this is going to be log base 2 of 2. B is the original base. This was the natural log, so it is base E. Okay. Now, we are also told simplify the expression using the fact that the log base A of A equals 1. So, let's take this whole thing, put it in here, log base 2 of 2, is going to be 1. Now we can simplify this fraction with a fraction to make it nope. There. Okay. And we now have an expression for k in terms of the half-life, and it's in base 2 logarithms. Plug your answer to part E into your answer for part C and solve for t. So we are taking our answer to part C, which is this one. Okay. Put that down here, and we'll get rid of our intermediate step. Take our answer to part E and plug it in. So that's taking this and plugging it in for k. So we're just going to select k and paste. And we are now solving for t. So take this, copy it down. Let's, the t's on this side, so basically what we have to do is multiply through by negative this. So I'm going to go ahead and do the negative part first. Get rid of the negative there, put a negative over here. Try to get the cursor in front. Negative. And we're multiplying through by the denominator here. So take that, and we are multiplying through. So I'm going to put it here at the end. And so that 1 over can go away. Now notice what happens here. We have a log base 2 of E and a log base 2 of E, so those are going to cancel. So we are left with minus the half-life times the numerator there. And we're simplifying as much as possible using the fact that the negative log of A over B equals the log of B over A. So that means we can get rid of this negative sign and flip the fraction we have here. So that's going to then take the denominator, replace the numerator with that, and then get rid of the sub-zero in the denominator. All right. So we now have an expression here for t. Almost there. The problem is that P naught is not something we can directly measure. So we want to look at we want to get this substituted out in terms of things that we can measure. Now, what is P naught in terms of P and D? Well, we actually gave you that earlier back in problem 2, but let's just think about it. If we think about it, every time a P goes away, it forms a D. So P naught is just the sum of P and D. So our expression here is I need a subscript. P naught equals P plus D. That's the answer to G. So we now say plug your answer to part G into your answer from part F in order to get rid of the P naughts. So we'll take our equation here, copy it down. We'll get rid of the intermediate step here. P naught becomes P plus D. There. It says separate the fractions within the logarithm. Okay. Equals, so we're going to do this again. Bring this over. Just for convenience, let's put in some parentheses so that we can see what we're taking the logarithm of once we separate stuff. If we separate the logarithm, then we end up here with that, but concentration of P over concentration of P is just 1. And there we have our expression. And indeed, why did the T1/2 get taken out? You're right, thank you. That was a mistake. Appreciate that. So the T1/2, should be in here and there. Yep, thank you very much for catching that, Amanda. All right, so check your work. Yep, indeed, it is the same equation. So now it's asking you to figure out, to make sure you understand what all of the parts of this expression mean. So T1/2 is the half-life of the parent isotope. What does this value depend on? So folks in the chat, tell me, what would you have to do to get a different half-life? It depends on the type of decay, exactly. So the half-life is a function of which pathway you are looking at, which isotope you are looking at. But that's the only thing it depends on. So if a billion years ago, the half-life was the same. That's the point there. Second question here about this. There are no quantities in the equation with a 0 subscript meaning initial conditions. However, T is measured relative to an implicit T0 equals 0. What physical event happened at T0? Be specific with respect to the zircon system. So for this, we need to back up here to the background information, and we see here that these facts together, which are some other things that are going on above, mean that any lead-206 found in zircon came only from the decay of uranium-238, which had been incorporated into the mineral at the time the mineral was crystallized from a melt. So the process that's being described here is that you have a melt. That melt has the right chemical composition to form zircon, There may be some uranium that's present and there may be some lead that's present. When it crystallizes, the lead, any lead that's in that melt initially is rejected, is kicked out. There is no lead present in the zircon. But there is uranium that gets present in the zircon. Then over time, the uranium is going to decay into lead, and so you now know that any lead that is there had to come from the decay of uranium-238. So time zero, when the concentration of lead in the system was 0, time 0 was when the mineral crystallized from the melt. So our answer to this, what physical event happened at time t0, is that the zircon crystallized from the melt with uranium present and no lead present. The ratio D to P does not have subscripted zeros. Given that, what does the quantity T represent? Represents the time since time 0 when it crystallized from the melt, which means T is the age of the rock. Any questions up to this point? Okay, so the last part here is trying to figure out, okay, I have this equation, which is really convenient for geochemists, but many calculators do not have a way to easily do the logarithm with base 2. Some calculators I know can do it, but many of them cannot. So J and K are about how do I do it on a calculator that can't do a logarithm of base 2. And to do that, we're going to use the change of base formula, which I had put right here. Bring that down. And so I'm going to take this formula, and we are going to replace the logarithm with the change of base formula. So this log gets replaced with that formula. That took the T1/2 with it, didn't it? Okay. Okay, I'll have to get it back in separately. All right. Bring, no, stop it. Okay, now we need to figure out the x, a, and b. So, chat, what is the x? In this case, we are going to do it in terms of natural logarithms. What does the x become? E. The natural log is base e. What is b in this case? 2, correct. Because it is the base that we used here. We see the b here becomes what we're doing here. A, what does a become? Yep, that's right. A becomes the thing you're taking the log of. Nope. There. And now we have an expression that can be plugged into a calculator that's because calculators have the natural log button. This is the same as ln. Log base e is the same as ln. K is saying do the same thing, but just with log base 10. So that's a 10, that's a 10. And so what this is saying now is that as long as you're consistent about which logarithm you're using in the numerator and the denominator, you can use any log you want for the formula to work. Now, are there any questions about this part? Okay, yes, I can repeat that. So notice that the only difference between this version and this version is the x that I chose when using the change of base. So this is using the natural logarithm in both the numerator and the denominator. This is using the base 10 logarithm in both the numerator and the denominator, and they both work. So so as long as you use the same logarithm in the numerator and the denominator, it doesn't matter which one you use. This formula will work. Okay, so now that you have this formula, whichever one you want to use, so you could take that one, for example, and you would then get rid of that intermediate part. And you now have a formula where you can just plug in the numbers. So you have a lead to uranium ratio that's going to go in right here. And you have a half-life that you look up from the table that you plug in right there. And then you do it on a calculator, or you plug it into Wolfram Alpha. And you get your numbers. And the answer, remember, this T is the age of the rock, the age since the rock crystallized. So, how to start 14? Sure. So the easiest way to think about this is to think about it in terms of ratios. So I'm going to grab this right here. And just put that part right here for a moment. Okay? Stop it. Now, let's remember what the daughter and the parent are. The daughter is the lead, the parent is the uranium. Suppose that 10% of the lead of the sample you analyzed in that question had leached out through microcracks. So that means that the amount of lead we have is going to be only 90% of what it should be. So we're going to take our ratio and we're going to multiply it by 0.9 over 1. Because we're not changing the amount of the parent ion, but we are decreasing the amount of the daughter ion by 10%. And that's it. You take the actual number, question 13, so you take this ratio here, that's this ratio, and you multiply it by 0.9. And that's pretty much it. All that's left is then thinking about what the answers that you get mean. So, that's pretty much the activity right there. Any clarifying questions? When is our next exam? We're supposed to have one this week, but the schedule changed. Yes, so if you look up on Piazza in the search bar, type in revised schedule, then you'll get a full list of all of the changes for the rest of the semester. The specific question here about our next exam is that I'm going to be releasing it on Thursday of next week, and we do the Sunday that's following that. So it will be due 2 Sundays from now. Can I change it on the syllabus? I will try to remember to do that. If somebody could send me a Piazza message, a private message to do that, then the next time I'm sitting at my computer with it, I'll know to do that. Have a study guide this go around. Yes. Well, so I will certainly have the list of topics like I did last time. I am going to be releasing to you the spreadsheet kinetic simulation example along with tutorial videos. I mentioned that at the beginning of class today, and I've been talking about it some last week. That's going to be released to you on Tuesday of this week. So tomorrow I should be able to have it done by then so that you can have it. With that, you will be able to practice the kinds of data analysis and calculations that are going to be on the exam. The tutorial video I'm going to use will talk about not only how to use the spreadsheet and how to use spreadsheets in general, because I know not everybody is a master at Excel, but it will also go through specifically how do you take the data, how do you do the plots of it to see, is it first order, second order, zeroth order, whatever, and then how to extract rate constants from it, rate coefficients from it, and then also specifically how to use the method of initial rates with it and how to use the method of flooding with it. Yes, this will be a main topic on the exam. So I will, on the exam, I will be giving you a new spreadsheet that will work in much the same way as the one that you're going to be getting as practice. And using that to generate your own simulated data, and you will then have to be analyzing it to determine the rate law. And you will be analyzing some proposed mechanisms to see which of them will be consistent with the rate law that you determine. So yes, this the main topic. This exam is covering 3 weeks worth of material. 2 of those weeks are kinetics. 1 of those weeks is the first part of equilibrium. The kinetics part is going to be focused around this simulated data and then analyzing it, which is why I'm giving you plenty of time to practice working with it on this practice spreadsheet. The equilibrium stuff, I have not fully figured out how I'm going to do that yet. It's not going to involve, it's almost certainly not going to involve that same spreadsheet. So it may have a system of some sort, and I will release, as soon as I get that figured out, I will release information about what that system is going to be like. I am indeed going to be trying to ensure that this exam is shorter than the first one was. I'm also going to be paying very, very close attention to the wording of the questions so that they are so that some of the things that I've been learning from the wonderful feedback I've been getting from you, so I can take that into account in making sure my wording is as clear for you as possible. Yes, I will still give you 3 hours, even though I'm trying to make the length of the exam in terms of number of questions shorter. So I really want you to not be struggling for time. So my goal is that if you are well practiced in doing the kinds of calculations that you need to do, and you understand the concepts, it will take probably an hour to an hour and a half to do it. Which means that if I do it myself and go through the calculations, it shouldn't take me more than like 20 minutes to 30 minutes for me to do it. That's the goal I'm going to be aiming for. I mentioned this at the beginning of class, but I do know that some people came into the chat after I started talking. So I'm going to mention again that on Thursday of last week, I did an extended exam-style reaction mechanism example problem where there was an overall reaction that had two different proposed mechanisms, and we went through analyzing both mechanisms and then talked about how you would then experimentally distinguish between the two, so to see which mechanism is more plausible. So I do recommend going to that recorded class video and looking at that extended example. In addition to that extended example, near the end of class, we had a little bit of extra time, and I posed another question that's analyzing a mechanism, and I let the class just work on it for a little bit, and then I talked through the solution to it. So that second one, after you watch the first one, would be a way for you to get some practice working through a mechanism. Later this week, if we are short on other topics to talk about, I am happy to run through that again if people would like me to. We have maybe 5 to 7 more minutes. Anything else on this, or should I go back to the muddiest points list? Is there a preference? All right, I will go back to the muddiest points list. All right, so some of the questions here. So we talked about these. And I mentioned having a list of equations that I hopefully will get posted this afternoon. Unimolecular reactions. Someone was confused about why they don't require a collision. So the idea of a unimolecular reaction is that you have some molecule that has enough kinetic energy of some kind that within its vibrations as its atoms are bouncing around, that it will on its own either break itself apart into like a fragment A and a fragment B, or it will undergo a rearrangement of some sort. So maybe you've got imagine having a double bond here, chlorine, chlorine, something like that, hydrogen, hydrogen. And then maybe it undergoes a reaction where it's going to rotate. So you end up with a different compound where the chlorines are opposite each other rather than being on the same side as each other. So these would be examples of unimolecular reactions that could happen. Now, it's not as though there are no collisions happening at all. The collisions that happen are how the molecules get enough vibrational energy for the reaction to happen. But it's not a collision specifically that is causing it to happen. It's the collision is giving the molecule enough energy to be able to get over the reaction barrier. So if you have a molecule that currently has this much energy, at this level, it can't get over the activation barrier. But then a collision comes along and gives it enough energy to be up here, then it has enough energy to be able to fall apart and go over to the reactant side. So that's what's going on in a unimolecular reaction. Okay. There are a lot of questions I've been seeing on Piazza about, I'm sorry, how is there a collision if there's just one molecule is asked in the chat. So it's not that there is just one molecule. You have an entire gas of molecules that can collide with each other. It's just that what determines the reaction rate isn't about how frequently the collisions happen. It's about what fraction of the molecules have enough kinetic energy to be higher than the activation barrier. So there are plenty of other molecules around to cause collisions. It's just the frequency of collisions isn't what is determining the reaction rate. Does that help clarify it? Okay, you're welcome. All right, so there have been a lot of questions on Piazza about homogeneous and heterogeneous catalysis and being able to tell the difference. The difference is very simple in terms of it's just about phases. In homogeneous catalysis, the catalyst is in the same phase as the reactants. And so if you have a solution and if the catalyst is a solute, then that is homogeneous catalysis. For a heterogeneous catalysis, the catalyst is a different phase from the reactants. So think of that like a catalytic converter in an automobile, for looking at the exhaust, where you have a surface of a solid, either platinum, palladium, or rhodium typically, and the gases that are coming over it are reacting on that surface. So you have carbon monoxide and oxygen gas that are adsorbing onto the surface of the catalyst, doing their reaction there, and then desorbing off the surface to become gas again. So that's what the difference between homogeneous and heterogeneous catalysis is. Homogeneous, the catalyst is in the same phase as the reactants. Heterogeneous, the catalyst is a different phase from the reactants. Now, given how many questions there have been on this in Piazza, it makes me feel as though there may be some Newton questions that are expecting something else about it, and I don't know what that is. So if somebody has a particular confusion about this, if you could post a screenshot of whatever question it is that's confusing, where that description I just gave isn't sufficient, that will help me answer that question a little better. Okay, enzyme catalysis. Can enzymes slow down a reaction? Well, if an enzyme does that, it wouldn't be called catalysis anymore. It would be called inhibition, because a catalyst, by definition, increases the speed of the reaction, whereas an inhibitor, by definition, decreases the speed of the reaction. So it would be called something different in that case. And then finally, mechanisms. We had, I was just talking about the extended example from Thursday last week. Okay. I am now out of time, so I didn't get to the equilibrium questions that we have here. So they will be top of the list to start on tomorrow, unless there are further questions that come up about the group activity. Those will come first tomorrow. The equilibrium will then be the second thing I will talk about tomorrow. And so you can take a look at those in the recorded class sessions if necessary. And as always, there will be the timestamps indices posted so you can get to it quickly and just look at the parts you're confused about. Thank you very much, and have a good day.